Hello and welcome to this R tutorial. So in the previous section, this PCA feature extraction technique reduced the dimensionality of our problem by extracting the variables that explain the most the variance. And now in LDA this is quite different. We are extracting some new independent variables that will separate the most the classes of the dependent variable. And therefore, since this time it considers the classes of the dependent variable, well, that means that it considers the dependent variable to proceed to this feature extraction technique, and therefore that makes LDA a supervised dimensionality reduction model. Alright, so now let's apply LDA on R. So first, very quickly, let's set the right folder as working directory. So we'll go to our machine learning A to Z folder, part 9 dimensionality reduction, and we are now in the section 44, linear discriminant analysis. So let's go inside, and that's the folder you want to set as working directory. We are still working on the wine.csv file, so that's exactly the same business problem as the one we worked with when implementing PCA, and so that will be a good opportunity to compare this dimensionality reduction technique, LDA, to the previous one, PCA. So now let's not forget to click on this More button here and set as working directory. Perfect. And so since we are working on the same business problem as before, as for PCA, well, implementing LDA here is going to be very easy. We will just take the PCA code, take everything from here down to the bottom, copy, and we'll go back to LDA and paste the whole thing here. And inside of this code, we will just need basically to replace this applying PCA section by a new section dedicated to applying LDA. So I'm going to remove all this section. So let's remove this and let's replace here PCA by LDA. And now it's time to implement LDA. So the package that we're going to use to apply LDA is the mass package, MASS, and it's actually a package that is by default in your list of packages. It's the package right here, mass, support functions and dataset for enables and replace mass. Alright, so as you can see, this is not imported, so let's import it by using the library command. Here we go, and mass this way in parentheses. Alright, we can already select this to import the package, and now let's implement LDA. So the first thing that we have to do is, as for PCA, create an LDA variable that we will use to transform our original dataset into this new dataset composed of the linear discriminants. And so we're going to call this variable LDA equals, and now we're going to use the LDA function, as simple as that, and let's add some parentheses. And now let's see the arguments by pressing F1. Alright, so the arguments are here. The first argument is formula. So that's exactly the formula of your dependent variable with respect to the independent variables. So far, the original ones. So here, as a first argument, we will input formula equals customer segment. Remember, that's the name of the dependent variable. And tilde, and we can add a dot. Don't worry, we don't have to write all the names of the independent variables. The dot is here for us. So, comma, and then next argument. And then the next argument is data. And as for PCA, the data here is going to be the training set. So let's add here training set. Here we go. All right. And actually, that's all. And that's for a specific reason, a very important reason that is directly related to LDA. It's due to the fact that LDA is a supervised dimensionality reduction technique. Remember, supervised means that the LDA model takes into account the dependent variable. And since it takes into account the dependent variable, well, it's quite intuitive to understand that the number of linear discriminants will be related to the information of the dependent variable. And that information is actually the number of classes in the dependent variable. And there is this explicit correlation between the number of linear discriminants and the information of the dependent variable. It's that there will be k minus 1 linear discriminants, where k is the number of classes. So here, since we have 3 classes, that means that we'll get at most 3 minus 1 equals 2 linear discriminants. So here, without specifying the number of linear discriminants equal to 2, we will get automatically 2 linear discriminants. And therefore, that's all, we don't need to add any other argument. So the LDA object is ready to be used to transform our original data set into this new one composed of the linear discriminants, we will get two linear discriminants, which is exactly what we want. As for PCA, we want two new extracted features, and this time these two new extracted features will separate the most two classes. So we should get very good results as well. And then that's the same as for PCA. We need to transform the training set and the test set so that we can then use them in the next sections. So we will use the training set to fit SVM, well, actually to the training set to build the classifier, and then we will make our predictions, predicting the test set results with this test set that will be transformed as well, and make the confusion matrix, and most importantly, we will visualize the training set and the test set results, something that we'll be able to do because we now have two features. Alright, so let's do it. Let's do the same to apply LDA on the training set and the test set. So first, let's start with the training set. Training set. So remember, we're keeping this name of the training set so that we don't have to change it in the rest of the sections. So training set equals, and then remember we need to use the predict function that's actually exactly the same as for PCA. We will, however, need to add something to make it work, and I will explain what it is, but definitely we are doing this transformation with the predict function. So parenthesis, and now inside this predict function we need to specify, the first argument here, which is the object. So the object is LDA, and then comma, and then the second argument, and the second argument is the data set on which we want to make the transformation, that is, extract the new features, and that's the training set. Here it is. So as a reminder, this is the original data set composed of the 13 independent variables, and this will be the new training set composed of the two new extracted features that are the two linear discriminants. Alright, so we can already do that to see if we get the right training set as we expect. So before executing this line, of course, we need to execute the previous sections because we need to import the data set and apply data preprocessing. So let's do it. We don't have anything to change here. Everything is already well prepared thanks to what we did in the previous section with PCA. So let's execute this. Here we go, well executed. And now let's apply LDA, create the LDA object, and then use this object to transform our original training set into this new training set composed of the two linear discriminants. So we already imported the mass package, so we just need to execute this line of code. Let's do it. Here we go, LDA object well created, and now we are ready to transform the training set. But before we select this line and execute it, we need to add this one more thing that I just mentioned, which is a function that we will apply to this whole predict LDA training set here, and that will set this training set that will be transformed into a data frame. Because for PCA, when we did this, when we transform here the training set to this new training set composed of the principal components, well, we got a data frame. But for LDA, that's not the same. We will get a matrix. And we need a data frame because then we have the next code sections, and inside these code sections, the functions that we use expect a data frame for the training set. Here, for example, it expects a data frame. And so we absolutely need to convert this transformed training set that will not be a data frame if we execute it this way, but a matrix. And so to simply convert this into a data frame, I think we already did it before. We need to use the function as.data.frame and parenthesis, and we close the parenthesis here, and that will set this transformed training set as a data frame. And now we are ready to execute this line of code to obtain our new training set composed of the extracted features, the linear discriminants. So let's do it. Let's select this line and execute. And as you can see, the training set is still a training set. Otherwise it would be in values. And when I click on it, let's have a look at what we just created. So first of all, the first thing that we see is this first column here. That is the dependent variable itself. I know this is no longer called customer segment, but it's actually the customer segment column. That's exactly the same one for the same observations and the same labels 1, 2, and 3. But automatically, it was called class by the predict function. So don't worry about that. That's the dependent variable. And then the next interesting thing we see are the two linear discriminants, LD1 and LD2. And as I told you, that's the number of linear discriminants we get due to the fact that we have three classes for the dependent variable. So that's what matters for us now, and that's the variables that we'll use, that's the new extracted features that we'll use to train the SVM model, to make the predictions, to make the confusion matrix, and eventually to visualize the results. And then we have this other three variables, posterior 1, posterior 2, and posterior 3. That is just variables derived from the LDA model equations. So that's not very important here. What matters is that we have our dependent variable class and our two new extracted features, the linear discriminants 1 and 2. And so now what we have to do is set our training set into the right format. That is, we want a training set that is composed of first the two extracted features, the two new independent variables, and then in last position, the dependent variable class that is nothing else than the customer segment. So basically what we need to do here is the same as what we did for PCA, that is, play with the indexes to not only set the right order for our columns, but also to not include the three columns here, posterior 1, posterior 2, and posterior 3. So what we'll do here to be efficient is take our PCA model, and we will take this line here, copy, and go back to LDA and paste that here. All right, and now, as for PCA, we need to include three indexes. This first index here will be the index of LD1, so that is the index of this column. That is 1, 2, 3, 4, and 5. So that's index 5. So let's add it here, replace 2 by 5. Then the second index here should be the index of the second new extracted feature, that is LD2. So that is index 6. This column has index 6. So let's replace here 3 by 6. All right. And eventually, this should be the index of the dependent variable. And this index is, of course, 1, because this is the first column here that has index 1. So now, when I execute this line, here we go, look at our new training set. Well, that is this time exactly what we want. The first two columns are the new extracted features, and the last column is the dependent variable vector, exactly as what is expected in the rest of the code sections. So perfect, our training set is well transformed and ready to be used to train the SVM model. All right, and now we need to do the same for the test set, so that will be very quick and easy. We will select these two lines here, copy, paste, and now we just need to replace training set by test set here, here as well, here, and eventually here also. And now we can just execute these two lines, but let's execute them one by one. This is the test set so far, composed of the 13 independent variables, the original ones. Then when we select this line and execute, well, we only get two new extracted features, LD1 and LD2, and the three variables here of the equation, and of course the dependent variable class. And then when we do this again, to take the right indexes in the correct order, we execute this, and now we get the test set composed of the two new extracted features in first positions, LD1 and LD2, and the dependent variable in last position. So that's perfect. Now we are ready to execute the rest of the sections to build our SVM model. All right, so let's do it. And actually, we don't have much thing to change. In this section, do you think we need to change something? Well, the answer is yes, because remember the dependent variable is no longer called customer segment, even if it is the customer segment variable, but this time it has a different name, which is class. And that's actually the only thing that we need to change, because the training set still has the same name. It's the training set that we just transform here. So that's fine. And then it's the same type and the same kernel, because we are building a linear SVM model. All right, so perfect. Let's execute this section. Let's do it. Done. Model created. And now we are ready to predict the test set results. So the test set results, do we need to change something here? Well, this time the answer is no, because we have our test set transformed. It has the same name and the classifier is this one. So everything is perfect. We are ready to execute this line of code. Perfect. And same for here. We don't need to change anything. We can just make the confusion matrix by executing this line. Here we go. Confusion matrix created. Let's see if we also get 100% accuracy. We will be able to see that in a flashlight, because if there is one incorrect prediction, well, that means that we will not get 100% accuracy as we obtained with PCA. So that means that it will not be as perfect as PCA. So let's do it. let's type CM here and press enter. And unfortunately, we get one incorrect prediction here. But that's not such a big deal because not only one incorrect prediction is still excellent, but also remember when we visualized the training set results with PCA, well, we had incorrect predictions. So we were just a little lucky to get 0 incorrect predictions with PCA. So alright, so that's still excellent results. And now let's visualize the training set results. Now, do we need to change something in this section? Well, try to figure out if yes we do, because it's important to understand this in case you use this code section here to visualize the result on your problem on your dataset. Well, the answer is this time yes, because this line of code here, call names, expects to have the real name of your independent variables, the new extracted features LD1 and LD2. So here we need to replace PC1 and PC2 by respectively x.ld1, because that's the name of the first extracted feature, the first new independent variable, and x.ld2, the second new extracted feature, the second new independent variable. So let's replace them, PC1 by x.ld1 and PC2 by x.ld2. So that's very important, and that's the only thing that you will need to change. The call names here must have the real names of your independent variables when you visualize the results. And then do we need to change something else? Well, this we can also change, but that's not compulsory. That's just for the labels of the x-axis and the y-axis. So let's do it anyway. And this time we don't need to specify the real name of the independent variable. We can just replace PC1 by LD1 to specify that it's the linear discriminant and not the principal component. And same here, we can replace PC2 by LD2. All right, and now that's done. Now this code is ready to be executed. So let's make the quick same changes for the visualization of the test set results. So let's replace PC1 here by x.ld1, then PC2 by x.ld2, and replace PC1 by LD1 and PC2 by LD2. And now everything is ready. We don't need to change anything more. We can grab a cup of coffee and visualize the training set results and the test set results. So let's do it. Let's hope that everything is okay. So I'm going to select all this section up to here. So that's to visualize the training set results. Let's do it. And here we go. All right, so it's executing. It's always taking a little time, but we will get there. We can already click on plots. All right, so the computations are being made. Almost done. And here are the results. Beautiful results. The three classes were almost well separated, perfectly well separated. We can see the incorrect prediction, but be careful, that's not the same incorrect prediction we saw with the confusion matrix, because that concerns the test set. Here it's the training set, so we also have one incorrect prediction on the training set. That's this one, but that's almost perfect, which is quite intuitive to understand, because as you remember, LDA tries to separate the most the classes of your dependent variable. So that's why here we can see that the prediction boundary is kind of equidistant to the majority of the green points here and the majority of the blue points here. So that's perfect. Each wine is in its correct segment of customers, and therefore this wine business owner can feel pretty confident at predicting for each new wine to which customer segment he should recommend it. And not only he can be pretty confident at recommending the new wines to the right customers, but also thanks to the feature extraction technique that allows him to visualize its results in 2 dimensions, thanks to this number of 2 new independent variables, the linear discriminant. Well, now this wine business owner can make a clear plot of its different segment of customers and putting in each segment of customers the different wines. So eventually that can be pretty convenient. Okay, so perfect. We managed to build a great LDA model, so we'll finish on this good note. And therefore we'll move on to the next section of this course, which is going to be another feature extraction technique, but this time adapted for non-linear problems. So since this problem is obviously a linear problem, because we managed to apply very successfully linear models as PCA and LDA, well, it won't be relevant to apply a non-linear feature extraction model on this dataset. So we will work on another dataset that is of course going to be non-linear. And this next new feature extraction technique that we're going to see is going to be kernel PCA. So I look forward to starting this in the next section. and until then, enjoy machine learning!